Okay, folks, I think it is about to start. So today we have the pleasure to have Professor Fei Miao from University of Connecticut, where she is Pratt & Whitney Associate Professor. So I had the luck also to be a colleague with her back at UPenn. So before being a professor at UConn, she was a postdoc at UPenn at the Precise Lab and GRASP Lab. And before that, of course, she was also a PhD student where we overlapped with Fei. So she has multiple awards. One of them is NSF Career in terms of the most recent career, and also Best Paper Award at ICCPS, plus an annual ICCPS Best Paper Award. So yeah, we look forward now for the talk. And yeah, it's a pleasure to have you here.
Okay, thank you. Thank you for the introduction. Yeah, feel free to come in. So it's my pleasure to visit Michigan during this nice weather. First time here. It's a really nice town. I have heard the reputation from many of my colleagues, and they said, okay, during my sabbatical, I must come here and give some talk and visit. So today we will mainly introduce our group's recent years' work on learning and control for safety, efficiency, and the resiliency of embodied AI. So we have seen a lot of opportunities provided by the current development of AI technologies. And for example, with large amount of historical data and real-time streaming data, we can provide better predictions for like a time series analysis. And especially our work, we have been doing a lot on reinforcement learning. So recent years, it has a lot of exciting results on different problems, like play this AlphaGo game, and especially for robots. So we have a lot of hope on, say, in the future, we can have all these kind of learning techniques to provide us better system solutions. Especially our group have been focusing on multi-agent learning and control. The motivation is in the future, there will be a lot of scenarios, say multiple robots, they need to coordinate with each other, finish some tasks, like in manufacturing places, in warehouses, and also in, for example, autonomous vehicles. So in the future, there will be like many vehicles on streets in this mixed traffic environment. And also we envision that if they can talk with each other, they can communicate with each other for this connected autonomous vehicle solutions, we can really improve the current transportation solution. However, there are still a long way to go to really have robots in our real world life. So for example, if we just do reinforcement learning, play some video game, we fail, that's okay. We just restart the game and do this infinite many times of a trial and a failure. But if it's a real system, then we have to make sure that it is safe enough. So if there is any accident, it might be like even dangerous to human life. And besides safety, efficiency is also another problem. So think about even maybe every single autonomous vehicle work very well, but if they don't understand how to coordinate in this mixed traffic environment, then together maybe this can be a very chaotic, not efficient system at all. So we need to think about, okay, how to really make the entire multi-agent system environment safety and also efficiency. So in terms of addressing these challenges, our group has been focusing on these 3 categories of topics. So we will mainly focus on the first, learning and control with communication capability for multi-agent systems today. So I will only briefly introduce our work on data-driven robust optimization and the cyber-physical system security. So for the problem we have been working on for learning and control with communication, we really want to understand the tridirectional relationship among communication, learning, and control. So using connected autonomous vehicles as some example here, so we can consider there can be vehicle to vehicle, it's like agent to agent communication, and there can also be like a vehicle to infrastructure communication. So the opportunities here is we have many sensors, and they can collect a lot of historical and also real-time data. And we also have smart actuators that can execute our control solutions. Basically, this is a data-rich environment. And of course, we have a communication capability here. So a lot of solutions are still developing, but indeed it's better than, for example, 10 years ago. And we also have still a lot of challenges to solve to really improve the efficiency and safety of the entire system. So one challenge is if we only consider like a single agent or single robot, it's okay to assume we have the good dynamic knowledge about the state transition of this system. But if we consider this in this multi-agent system scenario, from every agent's perspective, for example, we want every agent to have this distributed decision-making capability. Every agent do not really have this full system dynamic knowledge. We cannot just assume we know like the entire complicated systems like a state transition functions at every moment. And then maybe agent wants to do some learning-based technique to learn like how to behave in this scenario. And from that perspective, every agent will have like some uncertainties about the state knowledge of the entire system, and we have to consider that. And meanwhile, there will be safety requirements. Say every agent, they want to make sure that there's no, for example, no collision between agents, and also no collision between agent to environment obstacles, for example. And this will be a large-scale system. We want to make decision in real time. And also we want to understand through this learning and control process, what will be the benefit of communication? Does it really bring additional maybe reward or efficiency or safety guarantee for the system? Or it might just cost like a lot of time and energy to communicate, but does not really bring too much benefit to the system. So we really want to understand these questions. What will be the benefit of communication in this learning and control setting? So in the following slides, we will mainly introduce our work in these 4 topics. So we will, using this connect autonomous vehicle scenario as the main example to explain our technique, starting from this how we do uncertainty quantification for a collaborative perception among these agents, because nowadays a lot of like understanding of the environment through computer vision part. And if we really want to make sure, say, we have guarantee on all these like planning on the control side, we need to understand what will be the uncertainty on this computer vision part. And we will introduce our work on safe and scalable multi-agent reinforcement learning, assuming there will be like a communication among agents, and what will be the benefit of communication for motivate multi-agent system to communicate, and how we can design incentive mechanism for them. And finally, we will introduce our work on robust MARL and state uncertainties. For example, the state uncertainty can come from this computer vision side, right? So if we use computer vision technology to do object detection and trajectory prediction, this sort of thing, basically, if we have uncertainties from the state part, how we can do MARL algorithms. So now let's start from this uncertainty quantification for collaborative perception. So computer vision methods have provided us a lot of like fancy results, like for object detection, object tracking, trajectory prediction, etc. And recent years, they are also inspired by like how control and planning people do this multi-agent system methods. So they have also developed a lot of like collaborative perception methods. So it can show, say, with shared information through this computer vision part, there can be like improved accuracy on their prediction result. And meanwhile, uncertainty quantification in general for learning methods, there have, so this part. Maybe, I'm not sure. So this blocks the, yeah, so meanwhile, uncertainty quantification for machine learning algorithms is also a pretty hot topic recently, like especially like a conformal prediction, this sort of technique, and then people really want to understand, okay, given neural network-based prediction result, what will be our confidence rating on it? But conformal prediction method, the main focus is on after the training is finished and frozen the neural network part and how we can quantify the uncertainty. And what we analyze, we need on the vision side, say, okay, first of all, uncertainty quantification is important because just using this object detection as one motivation example, say if the learning-based method provide us prediction result like the red box, but if the ground truth is like the green box, and we just fully trust like the computer vision side, then it's possible we will plan some unsafe paths. If we know, say, okay, the learning-based prediction result or object detection won't be accurate anyway, and we consider, say, we use some orange ellipsoid to represent the coherence of the locations of each vertex, and we use a larger, for example, gray box as our prediction about the position of this object, and do a path planning according to the gray box. Then even the learning part is not 100% accurate, we still like have a pretty good chance to plan for a safety path. So that's our motivation of saying, okay, so if we have uncertainty quantification from the computer vision side, then this will be really helpful for planning and the control part. And then the question is, what will be a good uncertainty quantification method, right? So of course we can say doing a very conservative uncertainty quantification and making this very large gray box, but then it will be leading us to like an over-conservative result for maybe planning and control side. And if this uncertainty quantification is over-optimistic, like a lot of like a purely learning-based method, let's say using neural network and output some coherence matrix, usually that result is over-optimistic and say it does not really give us like a large enough gray box to define this uncertainty. So actually we need a good method to provide us this UQ result. And beyond doing uncertainty quantification, another question is, so if we specifically considering the uncertainty of the prediction result is important for our solution, then actually we also want to do some uncertainty reduction through this learning and model training stage if it is possible. So basically our key contributions and insight here is we quantify and reduce the uncertainty for this. For example, the first set of our work is on collaborative perception, collaborative object detection methods. And then our method can basically result in, we only need one inference pass during like the testing stage, and we will have uncertainty quantification result based on learning and also calibrated result. And we will show later in the experiment, say, basically this method can reduce the uncertainty of the perception part and also improve the accuracy. So the key idea is, in the training stage, we will have the part of direct modeling, say, the neural network structure for computer vision tasks may have like different kinds of structure. So we don't really manipulate like all these in the middle layers. We add several final layers in the neural network and also add additional output that represent the coherence matrix of the predicted mean of each location of each vertex. And we also revise the loss function. So for example, the original loss function may only care about the accuracy part, have some sort of like a mean square error. And here we define KL divergence loss style of error. Say we also want to reduce, for example, the deterministic value of the coherence here. So this kind of reduce uncertainty through the training stage. And meanwhile, as we mentioned, if we purely trust or rely on this learning-based uncertainty quantification result, it can be over-optimistic. The model say even the prediction mean is actually really far away from the ground truth. It can still result like a relatively small covariance, which is over-optimistic. So that's why we also have a bootstrap-based calibration process through training. So we will resample a subset of moving block time series data, and then doing the validation part, we will calculate, say, if we train the model based on this subset of data and what is average neural network prediction error, calculate the coherence, and then basically we will have a calibrated uncertainty coherence matrix through this retrain and validation process. And during inference stage, the final output coherence matrix will be including both the learning-based result and also the calibrated uncertainty, so plus, so to avoid over-optimistic. And the kind of calculation result we have will be like this. So for example, object detection, usually they will do 20 frames of this kind of bounding box in 1 second. And plus this object detection, we will also have like the same like 20 frames of uncertainty quantification through this inference stage. So basically you can see this orange ellipsoid to represent the covariance we will learn for the vertex position, and we can run our uncertainty quantification method on like a different collaborative object detection approaches. Like the live video shows, DiscoNet is some a collaborative object detection method that shares intermediate feature among different agents, and the right video shows what is called upper bound is a kind of collaborative perception method that assuming each agent share like the raw point cloud data with its surrounding agents. Basically our method, because it doesn't change much on all these like detailed neural network design part, we can utilize it for like different collaborative object detection tasks. And the lower video shows, for example, comparing sharing intermediate feature on the left part with the right part called the lower bound, so it only shares like the final object detection result between agents. So here basically we have the video to see our method can do this kind of real time during inference stage. And we also have some table to give you statistics result about comparing of our method with different uncertainty quantification method on different perception model. So for example, every column shows one kind of object detection method, and every row here shows the uncertainty quantification method, and the last row is our method. And we also compared with like some literature method, either say purely DM is purely based on learning-based method, direct modeling, only use a neural network to learn the covariance, and MBB is like only having this calibration part to estimate what is the prediction error for the model. And we can see that first table, we compare the accuracy evaluation result. So these IOU equals 0.5, IOU equals 0.7 are commonly used accuracy metrics in object detection tasks. So before we run these experiments, we have concerns, say, if we specifically put reduce uncertainty as one objective in our loss function, what if that affect the accuracy part, right? So what if like reduce uncertainty may like also reduce your accuracy? And after the experiments, we figured out that actually in many tasks, if we really care about reducing uncertainty, that will help improve accuracy. So the first table, we want to evaluate that, say reducing uncertainty, meanwhile, we can also improve accuracy. And the second table, we want to show, for example, our uncertainty evaluation, see on different models, what is the performance of our uncertainty quantification methods. And we figured out, okay, say our methods has the best like uncertainty reduction compared with literature methods. So basically say, if we have this modeling-based method in estimating uncertainty and meanwhile have some calibration process, then we basically have the best uncertainty reduction performance. And some other insights here also include, say, traditionally computer vision people, a lot of this kind of evaluation metrics actually focus on accuracy improvement. And there have been debate about, say, okay, if we want to do collaborative perception, what information should be shared according to, for example, what information has the best accuracy performance. And we want to kind of promote this uncertainty quantification also as a metric in a computer vision side, because what is uncertainty performance of this model will also affect like downstreaming tasks of planning and control. So we think in the future, like uncertainty quantification can also be one metric of deciding maybe at different scenarios, what information should be shared for this improving like a perception task performance side. And we also have this recent accepted paper by RAL, say if we have object detection part of uncertainty quantification, how can we utilize this information in the downstreaming object tracking task? So traditionally, the tracking task will involve algorithm like some common filter procedure to associate like this different object in different time frames. And usually the assumption is for common filter, we just assume we have some prior knowledge about, say, what will be the kind of occurrence of the object detection process, but actually there's no like very good way to calibrate that uncertainty. And in this paper, we provide the solution as, say, instead of just assuming prior knowledge, we will calibrate, we will utilize like our object detection part of calibrated uncertainty and use that as an input for this like a common filter and object association algorithms. And it turns out, especially for the cases when there are like a high occurrence, so it's like some object we lost it between frames. And if we consider uncertainty as this sort of additional information, then we will improve the accuracy a lot in these high occurrence objects. So if you want to check these like paper, source code, everything is online. So feel free to use it for your own problems. Okay, so now we want to see, after we analyze the benefit of doing like a communication for this collaborative perception and also doing this uncertainty quantification for vision part, what we can do in this decision-making part. As we mentioned that in this multi-agent scenario, it's hard for one agent to have full dynamic knowledge of the entire system. So our assumption here is basically we want to do distributed decision-making. We want to learn kind of a distributed policy function for every agent in this system. And our assumption here is basically every agent does not have the knowledge about like a state transition of the entire system. And here the decision every agent consider can be complicated. It's not just about, say, some centralized controller tell this vehicle, now you keep lane, now you do the platooning, and then I just finish this control maneuvers. It will be every agent needs to decide at different time frames and think about, okay, given my current knowledge about the state, and should I keep lane or should I change lane? And we will put this kind of discrete action on this multi-agent reinforcement learning part because it can deal with kind of model-free settings, say, without the state transition function. And there will also be continuous level of controllers, say if we need to doing keep lane or changing lane, what will be like the continuous level control input to finish this maneuver. And meanwhile, whether this is a safe action to execute or not, right? So what should be this part of dynamic control can teach or can help this MARL decision-making process. So this will be our problem setting. Kind of decision we consider will include both this sort of MIL part and also control dynamic system part. So first, we want to introduce some basic literature of the current research on MARL. So very similar to reinforcement learning in multi-agent reinforcement learning, assuming, for example, we have some simulator, then the setting will be every agent can explore its own action at a specific state. And then basically, they will have like some joint action to the current environment. And there will be a feedback about what is a reward function at this moment for every agent. The main tricky part or difficult part compared to the single agent case will be every agent's reward will also be actually affected by the other agent's state and the other agent's actions at this moment. So basically, even every agent have its own reward function Ri, but actually it can be affected by the global joint state and actions of all the other agents. So to understand the interactions among agents and among the environment, in recent years, very popular framework or algorithm for MARL is like a centralized training, decentralized execution. So for example, agent can learn very large scale Q function that related to the global joint state and action during the training stage. So the good part is, of course, agent get the information about like at this moment what the other agents will do and how will this affect its own individual reward. But the bad part is, even during training stage, if the number of agents is large or the number of state is large, then basically it still has this curse of dimensionality issue. So researchers have a lot of efforts to solve this kind of computationally or sample complexity problems in MARL and RL in general. And specifically for MARL, there have also been methods like purely localized policy functions. Say the policy function will only rely on localized state SI instead of like the very large global joint state function. And there have also been decentralized MARL algorithms, say, in this distributed optimization flavor, every agent train, again, a localized policy function. But the inner process of the algorithm actually still have this sort of consensus flavor. So it's like every agent will copy the parameter from all the other agents. And actually, the communication burden is also huge for this decentralized MARL algorithm to make sure algorithm converge on everything. So our research in this line of solving this scalability issue for MARL, the key different part compared with the literature is we don't go to this fully centralized or fully localized solution. Instead, we assume that each agent, they can, for example, share their state and action information with maybe the surrounding, get information from the surrounding NK neighbors through this training stage. And then the Q function we train will be kind of a truncated Q function that will be trained truncated Q function related to the NK neighbors state and actions. And theoretically, if we assume, okay, through all these training stage, the neighbors who share informations are fixed, then we can prove that the truncated Q function Qi, the approximation error compared with the global Q function that get all the joint state and action information, this approximation error can be bounded. And for theoretical proof, we just assume, say, okay, during this training process, these NK neighbors communicate are fixed. And in experiments, actually, we we relax that kind of assumption. So we basically simulate these cars and run randomly, no need to really have fixed neighbors. And I saw one question in the audience say, like, will the agent's objective to, what will be the agent's objective? Maximize the same reward function or maybe identical reward function? So here in this part of a proof setting, we assume that every agent can have its own RI reward function. So that's why they can train their own, like basically QI function. And of course, if it's like a common reward setting, then it will be all the agents want to maximize the same reward function. And then under that scenario, they only need to train one Q function. Yeah, that can be different setting.
Can you explain the relationship between SI and S capital NI?
As
the transition probability.
Oh, yeah, sure. So this assumption here means, say, for this single agent's transition probability is actually not relevant to maybe agents not communicating with it. So it's kind of like when you have a sparse graph scenario. So like when agents very far away from you, what the action it would take does not really affect too much on like your next state.
I can understand SI is the state of all agents, and S capital NI is the state of a single agent, right?
Yes. Yeah. So you mean like SI means like the state of agent I, and if no this superscript, it means like the state of the entire system. So this first part is about a scalable algorithm part, and later we will show its performance in experiment. And the second main challenges we want to solve for MARL is about the safety part. So there have been a lot of work on safe RL for the single agent setting. So for example, people can assume, say, the safety constraints is defined as some basically constraint function for RL, and then the problem turned to be solving unconstrained MDP. But for many real-world scenario, multi-agent reinforcement learning, so it's hard to say we just define one constraint function and work for like all these accumulated time step to quantify the safety requirements for the entire system. So how to define a good constraint function itself can be really challenging. So there have also been approaches like a state-dependent safety requirement. Then we will have, for example, formal methods to define what is safety requirements. And there have also been methods like a safe action projection. If RL explored some unsafe action, and then there will be maybe control-based method to project this action back to safety space. So for these methods, again, the problem is if in a multi-agent setting, there will be like objectives or tasks the entire team or system want to finish. And there have also been like safety requirements. So what will be a good like a problem formulation on like how to define the reward part, how to define the safety requirements? It's not very straightforward of just applying single agent safe RL frame to this multi-agent setting. And in terms of the safety guarantee part, our algorithm architecture is basically every agent during the training process will learn its own, for example, policy function. Basically, it's the actor neural network. The policy function will be a function of selecting action AI based on the current state information about every single agent. And also, for example, if they have shared state information from NK neighbors, then basically it will be based on the truncated state function. And every single agent AI is responsible for its own safety. So basically we want to make sure that in this training process, the replay buffer, we only save safe action in the replay buffer. So the algorithm procedure is we basically separate the reward part with the safety requirements. Say in the MARL, the reward definition is mainly about, for example, I want to improve the average speed of streets here, or I want to, for example, improve maybe the kind of comfort, or maybe reduce the travel time, etc. Put this sort of task-related requirements on the reward part, and then every single agent has, for example, a safe action mapping mode to check. At this moment, if I explore this learn changing or learn keeping action, is it safe or not? And after this checking, we only put safe action in the replay buffer to train MARL. If it's unsafe action, then this explored action will be excluded, will be filtered out, and will randomly explore another action. And after we figured out it is safe, we put it for MARL process. So basically, every single agent will utilize its own knowledge about its dynamic function and will use, say, this is my current estimation of the surrounding vehicle's positions, and I can decide whether, okay, currently I have some space to do this learn changing maneuver or not. So basically, each individual agent is responsible for doing its own like a safe action mapping. So the safety part, we don't have like a global information. Basically, every agent is responsible for its own. And experimental wise, so we first have this video to show the overall safe and scalable MARL algorithm setting. So this is a car simulator, and we train, for example, 10 vehicles together, throw them here in the simulator and see what will happen. And of course, we'll first try this kind of fully autonomous driving mode and see whether the safe actor critic algorithm work. And turns out, after training, these vehicles can learn, say, basically smooth driving, and at certain scenarios, just running in the same lane. And if this lane get a little bit crowded, they will also do some like a changing lane maneuver. they can drive smoothly. And of course, we also want to check this kind of mixed traffic scenario. We put some kind of like human driving vehicles. Basically, those are vehicles purely like controlled by the simulator, not controlled by our algorithm, and see whether our trained autonomous vehicle can behave very well. So again, as long as we're not putting like a crazy behavior here and relatively like enough space for the cars to do the maneuver, and they can still do smooth driving. Question?
What's the about scalability? So how is one difference in these efforts?
So I mean, training wise, we don't have a constraints. For example, even there are in total 100 agents, but actually the QI function only focus on maybe like a 3 to 5 communicating agents. Is relatively like a small size queue. We queue and actor the policy neural network we need to learn during the process. But in simulators, actually, we also have constraints about how fast the simulator can run, right? So for example, color, if we put like 10 vehicles, that's okay. If we put, for example, 30 vehicles, then it can get super slow. And also for like a 30 vehicle, we cannot do very fragile maneuver, this sort of thing. Yeah. So I mean, MARL algorithm wise, as long as it's like distributed, then we constrain say a relatively small size of queue and actor, then that's okay. Yeah. And also we have this obstacle at corner scenario to show the benefit of communication, especially in this like a traffic jam part. So without communication, then the autonomous vehicles cannot see there's already a jam at the corner. Once it reaches, it's already late to change lane. But if there is information sharing, then even vehicles relatively far away, for example, get the average velocity information of vehicles on this lane, and then it figured out this lane turns to be very slow. So it chooses to like change to a faster lane as action. So this shows in, for example, traffic jam scenarios, communication can help improve this efficiency of the network. And here we show some table results, say compare our truncated queue method with relatively slower, but say every agent has a centralized queue function MADDPG scenario to see, do we lose a lot of reward or not, not necessarily. So we can show that here our reward is very comparable to the case when the agent have like the interior state information. And here, for example, state, we keep it in like a low dimensional scenario. So it's like very basic position, velocity, acceleration information for each individual vehicle. And also vision information include, for example, final detection result of like this is a location estimation of the surrounding vehicles. And for actions, for MARL part of the action only includes like a lane keeping, lane changing, this sort of discrete action. And the reward here for the very beginning trial, we set up it as a common reward function for all the agents. Basically, the reward function is about to maximize the average velocity and the comfort of all agents. Comfort here, we set it up as say, if the agent is doing like a too many like lane changing maneuvers, then this is like a kind of aggressive behavior. So the comfort score is low if there are like many changing lane maneuvers larger than some threshold. So and for the safety barrier function, for the safety checking part here in this experiment, we specifically utilizing the theory from control barrier functions. So basically, we define safety requirements as maintaining a safety distance. If it's a lane keeping, then basically our safety distance is mainly about this longitudinal dimension. And if it's about lane changing, then we will care about the safety distance at the current lane and also safety distance, for example, to this left lane and safety distance on both directions. And we also want to show, for example, how this safety improvement helps in this MARL training process. So basically, if there is a positive headway, means, okay, we maintain the safety distance. And basically the red plot shows our algorithm performance, and the black plot shows the baseline. It's just a a regular MARL algorithm called MADDPG. It does not specifically have any setting about the safety part. For example, we can naively just set up a penalty for like any like collisions. And we show that only doing some sort of a penalty does not really have like a high safety guarantee through the training process. And this table shows like the number of unsafe actions awarded during training, because like there are 10 vehicles, many vehicles together, right? So if everyone just randomly explores, quite often say at least one vehicle may explore some like a collision behavior like that. So that's why like there are so many collision avoided during training. And we also want to show that having this safety requirement will also help in this improving reward part. So like the upper figure, the black plot shows regular MADPG knows this sort of safety action mapping part. So reward improves, but very slow. And the lower figure, the red plot shows, okay, so if we have this safety shield or safety filter during this training process, actually our algorithm can basically MARL focus on learn how to like improve the efficiency part. So this reward also increase pretty fast during the training stage. So this like empirical study about safety can also helps to improve systems reward. And then the question is, actually a lot of safety challenge happened in the scenarios like there are unexpected behaviors in this surrounding vehicle, right? So if all the human drivers behave very well and follow this our normal assumption or model about like trajectories or driving, then that's okay. We can have a 100% safety guarantee. But what if, like, say somebody ran the red or somebody park on the highway, right? These kind of abnormal behaviors. So can they improve the entire system's safety and efficiency, assuming that these green autonomous vehicles, they can communicate with each other, and how? And then our methodology here include two main parts. So the first part is about safety shield design, and it turns out that actually for dealing with this kind of unexpected behavior, we need a stronger safety shield. So this time, say we have some sort of like a V-square information for the front and the back vehicle. It's kind of caring about, say, what if there are like unexpected acceleration level of state change of the surrounding vehicles. So doing this sort of barrier function and the safety checking for the safety shield. And another important part is neural network structure that helps the agents to understand what is happening in the surrounding environment. So here we have this GCN graph convolution neural network, GCN transformer module. So basically it captures the spatial temporal correlation for the learning agent with its surrounding agent. So this GCN transformer neural network structure can deal with, for example, a changing number of agents, and also understanding like at different time steps, maybe some agent, the location changes, for example, larger than the others, and this becomes, for example, some agent we may pay attention to. So the neural network structure will help the agent to provide basically a better spatial temporal representation of this dynamic environment. And with both stronger neural network structure and stronger safety shield, what we can achieve is we show basically comparing of several folds. So first we compare with our method and baseline that without safety checking. So it's like we remove the safety checking module, but keep all these like a neural network structure the same. And what will happen is actually the safety rate will drop significantly, especially in this kind of like people running the red scenario. And here we show, say, if we remove the safety shield, what will happen in this like somebody suddenly parked on the highway scenario. So significantly drop in safety rate, and of course then reward, because once there is an accident, then the speed basically decrease significantly. And we also do some we also compare, I think, in this table. So it's about complete training results of people running the red or say suddenly park on the highway. We compare different neural network structure. So we keep the safety shield, the safety mode, every part is the same. The training algorithm and MARL same, just like a different neural network structure. And it turns out, again, this GCN transformer helps to improve both safety rate and the total reward of the system. And we also want to do some evaluation studies, say, what if we remove communication? Basically, it's like the car cannot talk with each other. So though algorithm-wise, they still train like a coordination scenario, want to optimize the same reward function, but we just remove their like some shared state information, what will happen? So keep everything the same, neural network structure, the same safety shield, but then without this communication, it will again significantly drop the safety rate. And here we also want to mention, say, in the training and the testing stage, we indeed like a change, for example, the number of agents in this environment. So we want to make sure that it's not say, oh, we train this neural network and it only work in maybe similar scenario during the training stage. In the testing stage, if we change the number of agents, it will still react properly. And we also want to emphasize in this red figures say actually a safety guarantee that very relevant to how challenging we put the testing scenario is. So if we say not doing running the red and not doing suddenly park on the highway, everybody like just drive smoothly, like in the very beginning scenario, then indeed we can still have 100% safety guarantees. And then the question is, we show that if multi-agents, they communicate and coordinate with each other, there have been like safety improvement, there have been also reward improvement. But the problem is, what if they don't want to communicate? They don't want to like coordinate, right? They might be from like different manufacturers and they might have different purpose and different maybe driving behavior. So sometimes to optimize system level behavior, an agent might sacrifice its own benefit. Like in this scenario, if vehicle D coordinate with vehicle C, let C finish this changing lane maneuver, then actually D is kind of yield a little bit to C. So then the question is, can we define some incentive mechanism to really motivate agents to share and communicate? So the method we designed here is called Shapley value reward reallocation scheme. So the key idea is traditionally in multi-agent setting, people believe that if we set common reward function for all the agents, then this is a cooperative game. So basically every agent maximize the same reward function. And the critic to learn during the actor critic algorithm is basically the definition of a Q function. But here we propose a different critic to learn. It is defined based on the Shapley value idea that this critic actually learn each agent's contribution to the entire system. So it's like a different coalition of teams. So the agent I participate with the coalition, coordinate or not, we compare the difference of the value. And then basically this Shapley value calculates the total reward that agent I contributes to like different correlations in this entire system. So Shapley value itself is a very classical idea in cooperative game setting, and previously is mainly for like a static game, not for this sort of like a sequential decision-making process. And also it has been utilized a lot in defining data and features value to improve one machine learning model's performance in supervised learning setting. And here is the first time we define in this reinforcement learning setting, multi-agent reinforcement learning setting, how we can utilize the idea of Shapley value to basically quantify if one agent participant in the coordination or not, what will be its contribution to the system. And we can prove that first, this Shapley value-based reward reallocation scheme, it is efficient in the sense that the system's total reward is completely distributed to each agent for cooperative policy learning. And we can also prove that if this value function of the Markov game satisfy the max game definition, then Shapley value is also a stable reward reallocation in the sense that our agents will choose to stay within the collision, communicate, and cooperate to optimize the objective. And we validate or test our Shapley value critic algorithm again in similar CV setting. And here we compare this Shapley value-based critic function with basically every agent have a common reward setting. And we can find out that actually the total reward of the system can be improved in like a different percentage of, for example, human driving, autonomous driving scenarios. And we basically use this one to show that if we kind of allocate the reward better, if some agent contributed to the system's entire reward improvement more, then we kind of allocate the reward back to the system and incentive it to communicate and coordinate, then we can train a better like a cooperative policy. And now we want to introduce our last part, our most recent work on robust MARL and state uncertainties. So the motivation comes from the scenario, say, if, for example, in our state information of this autonomous vehicle setting, we have like positions and velocities of the surrounding vehicles. So what if the state information has an error? And then basically our agent's policy and our agent's selected action will be affected. And in this multi-agent setting, so it can even like cause dangerous to the system. So in the previous literature, people have studied reinforcement learning, robust reinforcement learning, mainly for this simulation to reality gap issue. And the analysis is, okay, so the simulation to reality gap can be defined as the transition function or transition kernel uncertainty. So there's not much study on this kind of state uncertainty for RL, and there is some recent work on this setting of state uncertainty for single agent RL, but there's no study on, say, in this multi-agent setting, if there is a state information error, what will happen? So our analysis is we first define this problem as basically a state adversarial Markov game in the setting that there will be an systems agent and also an adversarial agent. And every system agent, this time, we first start from this common reward function setting. Say our system agent want to maximize the common reward function, and all of these adversarial agents want to like minimize the reward function. And the difficult part will be system agent does not have the true state information. It only has perturbed the state information. And adversarial agent instead has the true state information. Its action will be choosing like where or how to perturb the state. The only thing we know about perturbed state is it's still within the state space, right? So if the perturbed state is already outside of the state space, then we know like something abnormal happened. So the first step is we define the equilibrium concept as robust equilibrium in this setting. So it is in this Nash equilibrium scenario as, say, if only single agent deviate from its equilibrium policy, then it cannot gain a better payoff for itself. And the main different part will be the agents do not share like the common state information. Adversarial has true state, but system only has perturbed state. And we can prove that in very special scenario, in very special case, this robust equilibrium exists. For tabular case, for this finite state and action scenario, when there is bounded reward function, and we assume when there is a stationary state transition and reward function, when state perturbation function of the adversarial agent satisfy a bijection function, then we can prove this robust Nash equilibrium exists. And also we can prove for finite state action space case, the Q learning algorithm can converge. However, this state perturbation in the real world, it can actually be arbitrary. So it's hard to say, okay, it satisfies some bijection function. So then for a more general case, it will be, say, the robust equilibrium does not really exist, and we cannot use that as kind of an objective or solution concept for the agent to calculate the policy. And when the robust equilibrium does not exist, basically every agent can do solving this maximum problem as basically maximizing its worst case expected reward when it does not have much knowledge on this adversarial side. And we can prove that this maximum solution exists. And algorithm-wise, basically through the training stage, we are doing a gradient descent ascent style of algorithm. Say we put adversarial in the training and the agent maximize the reward, adversarial minimize the reward, and each agent learn its own policy function. And we can show that if we specifically, we consider it is possible, say the state information is not true, and consider that during the training stage, and when in the testing stage, there is like a different level of perturbation. It can be either random noise and different magnitude of noise level, or it could be a well-trained adversarial to perturb the state. Then we can show that this kind of MPE environment testing, kind of common baseline for MARL algorithm. And we can show, say, our algorithm outperform several baselines when state perturbation happens. And if you want to check all the detail of the proof, these papers are both online on TMLR recently. And then the final question is, I think this is still ongoing work in the future, that as we mentioned, say, when there is state error or state perturbation, if it's only carrying some reward, like say in this MP environment, that's okay, so reward is the only thing. But if it's in this kind of real physical dynamic system, then the safety part will be a big issue actually. So if the estimation about surrounding vehicle's position is wrong, then it's possible, say, we just goes to like some path and we'll have a collision. So then our method is safe and robust MARL algorithm design under state perturbations. So the basic idea is for this MARL algorithm part, we have this kind of maximum term in training the Q function. It will has this kind of regularized Q function to represent the case, say, our estimation about the state is not like accurate enough. And in the safety shield part, we also have a robust control barrier function to represent the scenario, say, our system state knowledge is not accurate enough. And again, we can show in different like experiment setting, if we perturb the ego vehicle's knowledge about the surrounding vehicle's position and the velocity, what will be the collision-free rate, compare our algorithms with baselines that have like a safety shield, but not a robust safety shield. So, so here is our test bed. So we, besides beyond the simulator, we also have this kind of F-intense vehicles, and we can do single vehicle, do this kind of tracking lane charging maneuver. And we also have like a simulator where basically say two vehicles communicate and coordinate with each other. And summary and some insights for today's presentation is we show that communication is really helpful for even starting from the perception stage, like collaborative perception, it can improve accuracy. And also, if we really care about uncertainty part, we can design algorithm to basically reduce the uncertainty and also quantify the uncertainty. And uncertainty quantification itself can also inspire the communication part. If we using both accuracy and uncertainty as metrics, we can decide at different scenarios, like what to communicate. And what is the value of information on the perception side. And meanwhile, communication helps to improve the safety and efficiency of the entire system in both normal and challenging driving scenarios. And in the future, we believe that uncertainty quantification will bridge the gap between computer vision, between the perception stage to this planning and control part. And considering how we can utilize the uncertainty quantification information from perception part, I believe that in the future, safe and robust MARL will still be like some ongoing research topics. And very briefly, for data-driven robust optimization, the scenario we consider is for mobility on-demand service. If we have electric vehicles to provide this sort of Uber and Lyft style of service, what we can do. And basically, we will just considering, say, the passenger demand side, our prediction have uncertainty, and also EV supply side has uncertainty, and how to deal with these two parts of uncertainty in our charging and passenger picking up scheduling algorithm. So we have been working on distribution robust optimization technique, and also robust multi-agent reinforcement learning methods for dealing with this kind of challenges. And we've also been working on several physical system security. The idea is for physical dynamic systems like cars, like power systems, we also have some knowledge about the system dynamics. And actually we can utilize that part no matter in game theory setting or in reinforcement learning setting, and to help us, for example, detect attacks and also say design resilient control algorithms and under like different scenarios of attacks. And here are my students and the collaborators. And I think in the future, our group will still focus on this learning and control method design to really provide safe, efficient, and resilient solutions for embedded AI. And I envision that we will continue to work on, for example, uncertainty quantification to bridge the gap between the perception society and the planning and control society. And also meanwhile, focus on this safe MARL, robust MARL to really promote this method in real world applications. I think I will stop here and for more welcome for questions. Yeah.
Okay, I think just because of the time and I don't see extra questions on the chat, or let me give some time for questions on the chat, and let's take only question one from the audience, and then we have the chance to talk to the speaker, you know, after releasing the room. Yes, please.
Yeah, cool. Yeah. So I'm just wondering, when communicating the raw data, when communicating the features, what would be the communication throughput and what would be the delay?
So it depends on like what we are communicating. So for example, if you only communicate like a basic safety message, like velocity position, this sort of thing, the delay is maybe within like 0.1 second or something. There, I think this part, there are still study about like communication wise, what we can do. And there can be different communication mechanisms. And for computer vision part, there's also been some survey paper showing, say, if we communicate raw data or communicate, say, compressed data or communicate, say, feature space, what is experimental wise data about the communication part. So I think indeed that will be some problems we need to consider. And our first step is we want to show if this communication, this information can arrive within this decision-making time frame, and whether it's helpful or not. So if it's helpful, then we are currently studying. So for example, we didn't show here, but in experiment, we have simulated cases like, okay, at some time steps, the shared information about like a position velocity actually does not reach to specific agent, how much it will affect, etc. So empirically study-wise, we have tried that. So it really depends on scenario. So if it's like just everybody's normal driving, that actually does not affect much. But if it's in like an obstacle in the corner, or say in very challenging scenario, maybe some accident happened, then if there's delay, then it will indeed affect the performance. Yeah.
So let's thank the speaker once again. Please come for questions. One here. Just.
Okay. So I think that question is about reward.
I think you answered the question here.
Yeah.
Right?
Yes. Okay.